So yesterday I talked about some conjectures on singularities that come in the minimum model program, and in particular I would like to focus on inversion of adjunction and explain how arc spaces can actually come into play to understand these problems. So suppose I'm going to focus on a smooth case. So suppose X is a smooth complex variety. Say dimension n. And I want to look at a divisor. So this E will be a prime divisor on some model Y. So this is a thing about as a resolution onto X. And suppose maybe I pick up an integer greater than 1. So the reason why I focus my attention on E is that the invariance of singularity that we defined yesterday depends on the divisors over X, divisor on models like over X, and maybe on some integer. So the focus will be on divisor evaluation. So for me, divisor evaluation is just a multiple, positive multiple of evaluation associated given by the order of vanishing along E. And to this, I would like to associate a subset in the arc space. I'm going to note by C, Q, X of E inside X infinity. I want to think about this. I mentioned this on passing last time. I want to think about this as a sort of a center of the evaluation in the arc space. So of course the center of evaluation is defined on a variety, but somehow this is a sort of a way of thinking about this set. That will not be the name, though this is commonly used in the literature. So I will use a different name. This is also very natural. So one thing I need to introduce, I was introduced in one of the talks yesterday in the afternoon, is the notion of a contact locus. So suppose that I have Z inside X, closed subscheme. And maybe I also, again, fix some integer Q. And I can consider the contact locus of order Q associated to Z. It will be just a set of arcs, gamma, inside X infinity, such that the order of vanishing, or if you like, the evaluation defined by gamma, evaluated on the ideal sheaf of Z, is exactly equal to Q. So this is a subset and in the arc space. And the idea is that you can use contact loci to define this set in the arc space. And the way you do it is as follows. So we saw a diagram like this already when we were discussing the Nash problem. So I look at the arc space of the variety X, and on the other side I have a resolution, some model Y, and some divisor E inside here. And what I can do is I can look at the arc space of Y. If this map is F, then I have an induced map on arc space, it's given by composition, that's F infinity. And what I'm going to do is that I'm going to look at the contact locus of order Q of E inside here. And then on the other side, I define this set CQX of E, exactly the way I define these components in the Nash map. So what I'm going to do is I take the image of all the arcs from E, from X, touching E of order Q, look at the arcs and the image in X, so this under this map. So you look at F infinity, F infinity, or this contact Q of E, and then I close it up. I take the closure, and it's easy to see that this is an irreducible set because I start with with a resolution. So this is an irreducible set, and this set is also the closure of the set is irreducible. And so this is called, the definition is that this we'll call a maximal divisorial set. And of course, associated to the evaluation, corresponding to the evaluation Q times the evaluation of E. So let's make some remarks about some obvious properties. So the first one is that, well, the first, for instance, if I take Q equal to 1, so I'm looking at arcs which have order of contact 1 with E, and up to taking a closure of the set, that's the same thing as just taking the arcs that goes through E. Because, again, we are on a smooth variety. And so you see that this is actually the same thing as what I was denoting by NE yesterday. On Monday, there was coming a Nash problem. Another observation, which is kind of relevant, is that this set only depends on the valuation. So in the construction, I'm using a choice of a model and a divisor representing, giving the center of the valuation, but I could have taken another model and a proper transform of the divisor on some other model. And it doesn't matter, you still define the same divisorial set. And in fact, more precisely, if I look at alpha inside here to be the generic point, then the valuation defined by this generic point actually is equal to the valuation I started from. So, and the reason is very simple. The point is that the generic point from here it actually is the image of the generic point of this set. And that is exactly an arc which is the largest possible arc with order of contact Q with E. And then you just think about this, you put back in functions, and you get exactly this claim. And the theorem that was mentioned in yesterday's talk in the afternoon, let's do to ein, Radersfeld, and Musata. It says the following. This set here, this set CQX of E, is a cylinder of codimension. Q times K of E plus 1. So let me remind you what KE is. So here, KE, also denoted by KE over X, is just a discrepancy. So it's just the order along E of the relative canonical divisor, which is in this case is really the order along E or the Jacobian of the resolution. And I'm insisting in writing in this way because this is really the right number that comes in the proof. Meaning that I'm talking here about a smooth variety, and one can ask about some similar statements when X is a singular variety. There are serious complications, but something can be done. The only thing is that I will not look at the relative canonical divisor. That might not even be defined. I will always look at the Jacobian of the resolution. So maybe I should remind you or tell you for the first time, if you were not here yesterday afternoon, what a cylinder is and what the codimension of a cylinder is. So the definition is that cylinders in the arc space of X are sets of the form C is equal to the inverse image on some level M of some set S. This is in set Xm. Oh, sorry, this is in set X infinity, where I look at the projection or truncation map by M to level M, and the set S is a set here. So this is the image of, inverse image of that, and this set is a constructible set.
I'm confused.
Yes.
X is smooth, and you take a resolution.
Well, what I mean by resolution is just the defining properties. So what I want F to be is a proper birational map. Yeah.
And the theorem is for any Q or just for Q sufficiently large?
No, this is the theorem is true in general. So for any Q, I look at a set and have that codimension. So in particular, this is already interesting when Q is equal to 1. And then I'm looking at one of these Nash sets and have some definition on. Of course, here I'm talking about a smooth variety. The Nash problem is interesting in singular case. So there will not be a good measure of codimension in that case. So these are the cylinders. So you really imagine that the arc space is the inverse limit of these towers of affine bundles, and a cylinder is simply something that for a certain level on, it just goes up as a cylinder. So it's a very clear definition. And so it's something defined by finitely many conditions. The condition given a constructibility. And in fact, these are in the Grothendieck language. This is the constructible subset of the arc space. Which doesn't mean that closed sets are like this. A closed set can be given by infinitely many conditions, so one needs to be a little bit careful about that. And so let me put some remarks here. So X infinity has a topology, if you like, the Zariski topology or the inverse limit topology. And as such, I can define a set to be irreducible, to be closed, open, and so on. And it's not hard to see that a cylinder C is irreducible, or is, say, closed, if so is the set S. In fact, if and only if. And in the codimension of C inside X infinity, so how do you define a codimension? Well, I really want to think about a codimension. I mean, if you like, the topological codimension, so it's the largest length of a chain of closed sets, reducible sets, from C all the way to X infinity. So, well, that will be equal to, or if you like, that's the same thing as the cool dimension of the local ring. Well, that will equal the codimension of S at the final level M. So it will be independent from there on. And so if you like, another way of writing this is something like n plus 1 times the dimension of X, which is n, minus the dimension of S. So one can actually think about this being the definition and then observe that this is compatible with the topology, or you can use the topology to define these notions and then just check that these are the same. Maybe it's more natural for me to do in that way, but it's really equivalent. The important thing is that implicit in this observation, the way you want to go, is the fact that this is independent. These notions are independent on which level I'm taking the cylinder, because I can actually go one level up and then consider the set over there and pull it back. And the reason is that implicit here is the fact that these maps from xm to xm minus 1 are bundles, am bundles. So now if you just look at this definition and you see how these numbers vary as you go one step up, you see that the definition is well posed. So I use the proposition. It says the following. If C is a cylinder inside X infinity, and suppose that C is contained in the following contact locus. You look at the contact locus of order E. This is inside Y. Sorry. This is inside Y infinity. So I'm still using that diagram over there. So I look at the contact locus of a relative canonical divisor of order E, or if you like, of a Jacobian. Actually, more important, it would be the Jacobian of the map. And then it follows, then if I take the image of C, this is a cylinder in X infinity of codimension equal to the codimension of C inside Y infinity plus this number E. So this is really an important fact. So somehow you think about cylinder, the codimension of cylinder, telling some information about the topology of the arc space. I already mentioned that the map F infinity is almost everywhere a bijection. For most we care, we can look at it as a bijection. But it's really changing the topology, and this is reflected in the fact that the codimension is changing. So the key lemma to prove this fact is the theorem of the Nash and Loisel, which has been already mentioned several times this week. So let's look at the following set. Let's look at the set. Well, I'm going to actually have to break the lemma, but anyway, you follow me. So let's look at the set sigma EM to be all the jets in, let me call it, maybe give some contact locus of order E, but at level M of the relative canonical divisor. So this is all the jets in Ym such that the order and the valuation, no, we call it order here, along gamma of ky over x is actually equal to E. So I need to be a little careful. So an arc, we saw the arc define evaluation, where jets also define evaluation. The only thing is that M jet will define evaluation from 0 to M, and then you put infinity. So in order to make sense of this, here I'm assuming that M is greater or equal than E. So let's see what the lemma says in general. So you just look at those sets. So those sets they stratify most of the jet schemes. Although there's maybe some part that is a smaller part that may be kind of irrelevant. So if I take M actually big larger, say twice E at least, then I can look at the following diagram. I look at, so I have a map on jet schemes, also given by composition. And then I have a truncation map, which you get E times down. And somehow I want to understand this diagram, because if I understand this diagram, then I can actually go up and understand how cylinders behave under F infinity. So inside here, I have a set, this set of contact locus with the Jacobian, sigma EM, and I can look at this image, which is will be sigma E M minus E. This is where I'm using that M is a bit larger. But I can also look at the image going down this way. So there will be Fm of sigma ME. And so what the lemma says is it gives us information about these two fibrations and how they relate to each other. And this is really a key, very important property. So this vibration here, the fibers here, if I call this map phi for simplicity, are the same as the fibers of phi, and these are equal to some copies this vibration. So we know that what the fibers are is m minus e times n, because we know these are towers of n bundles. But the important thing is that this is the union of these fibers, of this vibration. And how about the fiber of this map? Well, this fiber of this map are actually copies of AE. So this is a sort of a stratified vibration over here, where the fibers are these affine bundles of a fixed dimension, and that's given exactly by the order of Jacobian. And then there is another important observation, is that these fibers are contained inside these fibers. And so this is a formula. This lemma is at the base of the change of variable formula in motivic integration. And so what we are doing here is that by proving this theorem, if we are extracting from motivic integration the geometric essence that we need to understand the singularities. So now let me sketch of the proof of the proposition. I'm not going to try to prove the lemma. That's will take a little longer time, but I can give an idea of how using these lemmas, using this information on the fibers, you actually prove a proposition like that. So the idea is that, again, you look at this cylinder as an inverse image of some set M, S, where now pi m for me denotes now the map from y infinity to ym. And so maybe I can put a little y somewhere to remember that. So, and S is some constructible set inside here. So what I'm going to do is I'm going to take M sufficiently large. So if I given an M, I just can replace it by a bigger M by just taking the inverse image at that level and then rename that S and then go on. So if I do that, then what I can assume is that S is a union of fibers of the map from ym to ym minus e. But then the lemma implies that S is also a union of fibers of Fm. This goes from ym to xm. Okay, so now we can look at the image of S inside xm. So now you have a vibration. You know, Fm induces a map from S to this image to S. And so what do we know about this? Well, this is the fibers. So this is a, well, let me actually, if I say piecewise trivial AE vibration. So these are constructible sets. The way the fibers they come together actually is a bit complicated. Sometimes they don't really deform continuously. There are some jumps, but there is a stratification for which then becomes a nice vibration. And this guy is also constructible by Chevalier's theorem. So now a constructible set inside xm. And what left to prove, they can check, and maybe using the key lemma or using the fact that X is smooth, we simplify some arguments, is that the image of C, well, that by definition will be the image of the inverse image. Maybe I should have put a Y here. Of this set S. The idea is that there's a good diagram there. I don't have the right diagram, but I am, so here's the diagram, I guess. So I have a set S here, and I'm trying to get here. And I can go this way, I can go that way. And it turns out that by using this key lemma, you can check that this actually is equivalent. So there will be something like pi xm inverse, or the image at level m of S. So now this is a cylinder. So that's the idea of the proof. So there is another important remark about cylinders that we need to be aware of. So that's the next proposition. So suppose I give you a cylinder C inside X infinity, and say this is a cylinder, and properly contained. In X infinity. So it's not empty, it is not a whole space. So then C is not contained into the arc space of Z infinity of Z for any proper subscheme Z inside X. So maybe make a picture. So this is X. The cylinder is a set of arcs, a family of arcs on X. What I'm saying is that there is no way to pick up a subscheme Z so that all the arcs are contained inside Z. Sometimes, at a certain point, most of these arcs actually will stem outside of Z. Maybe the higher contact, I don't know that, but will not be fully contained inside the arc space of Z. So, in fact, one can show that the codimension, if you like the topological codimension of Z infinity inside X infinity is equal to infinity. From the point of view of motivic integration, the infinity is a set of measure 0, whereas the cylinders have a positive measure, so it will never be contained in any of these sets. In particular, if alpha inside C is a generic point, then if I look at a defined valuation along C, by definition, to be the valuation along this arc alpha, and this is a nice valuation. On X, on the function field of X. So what I want to do now is to actually state again the theorem of Einladers and Mustafa in a more precise way. So let's see inside X infinity be a cylinder, be actually an irreducible. Oh yeah, maybe I should have mentioned. Actually add it here. In particular, if C is irreducible and alpha is a generic point, Of course, if it's not reducible, then there are more than one generic point, so we don't quite get a evaluation. But I focus now on irreducible cylinders. So suppose that C is an irreducible cylinder. Then what can we say? So the first is that the evaluation of defined by C. So there are many interesting evaluations that come from arcs. For instance, if you take the arc given by some transcendental proper series, there will be some interesting arc that may actually define evaluation of a function field, but it's not a divisor evaluation. So you can actually pick up some interesting examples. But these kind of evaluations, actually, they are very familiar. They are just divisor evaluations. So this will be equal to Q time evaluation of E for some Q and some E. So it is a divisor evaluation. The second information is that, in fact, C is contained inside this maximum divisorial set associated to the evaluation. And therefore, because we already stated what the codimension of this set is, if you have something contained, you see that the codimension of C inside X infinity is greater or equal than this Q times KE plus 1. And with equality holding exactly when you have an equality here, up when C is dense, if you like it, in as soon as closed. So this explains the terminology. So all these are divisorial sets associated to the divisor evaluation. And this one is maximal among all of them in a sense under inclusion. So let's see some applications now. So one theorem that was stated yesterday afternoon is the following. It says something about low-canonical threshold. So since I define low-canonical threshold for divisors, let me stick to divisors. So suppose X is a smooth variety. And suppose that D is an effective Cartier divisor on X. And or more generally, any close-up scheme will do. Then the log canonical threshold of XD is the minimum over all M of the following number. You look at the codimension of, so you look at the jet scheme of D. So D, consider D as a scheme itself. So you look at the jet schemes of D, and this sits inside the jet schemes of M. Look at the codimension of this set. You divide by M plus 1. So, what is the idea? It is the following. So, for every M, you look at dm inside xm. So, these are the m jets of x, and then the one that lies fully inside D. And suppose that you look at S inside here to be an irreducible component of this set. And then I'm going to take C to be the cylinder over this component. So this sits inside X infinity. So what the theorem is telling us is that the evaluation along C can be written as Q times the valuation along E for some Q and some E. And therefore, we have the Q times KE plus 1 is equal to the codimension of S inside X infinity, is inside Xm, because that was the codimension of the cylinder, which is the same as the codimension of the set over which this is defined as a cylinder. And also, we have some information about the order of vanishing. So this maybe the new observation here. So if I look at an arc inside the cylinder, and I ask a contact order with D, when I project down level M, I realize that all the Taylor expansion up to level M, they all vanish identically on D. So this means that the order of contact is at least M plus 1. So this is the second observation. And the second observation is that Q times the valuation of E of D is at least, oh, this is a less or equal, and this is at least M plus 1. But now if you put this together, because the log canonical threshold is defined as the infimum of log discrepancies of evaluation, you see the log canonical threshold of xd is less or equal to all these numbers that I pick up in this way, which is therefore the codimension of, in Xm, of this component S over M plus 1. And I take the, let's say, infimum over all possible M and all possible S as above. And, well, that's the same thing as the infimum over all possible M. I just look at all components, so look at the codimension inside Xm of dm divided by M plus 1. And so this proves an inequality, and then in order to get the quality, you just realize equality by a divisor E that computes the log canonical threshold.
Can you express this directly in E infinity?
Not quite, I think. I mean, the information is there, of course. Information is gotten by looking at the maximum individual set. But somehow, again, given a maximum individual set associated to E, so if E computes the log canonical threshold, then 2E, so twice the valuation of E will compute the log canonical threshold, 3 times the valuation of E will compute the log canonical threshold. So if you really want to trace the kind of information, actually it's read at the level, at these final levels. And as you increase Q, the information will run away. So maybe a way of trying to understand information on the infinite level would be to look at the limit of this contact set, where you fix E, the right one, and you let Q go to infinity, take the intersection. But then will be something more complicated that could I mention, because that's infinity. So somehow one needs to estimate how fast it goes to infinity, I guess. Okay, so the next theory I want to talk about is the theorem of Ein, Mustaza, and Yasuda. So this goes back to the problem of inversion of adjunction for minimal lot discrepancies. So that was really the focus of my lecture yesterday. And so let's try to see. I think that this actually is very interesting, because you see, this theorem, so what this theorem does is give an jet scheme interpretation of an invariant, you understand. What this theorem is going to state today, now here, is not going to give so we're going to use arcs to prove a statement which is arc independent. So from this point of view, it's probably more interesting. So here's the stating. So X, again, is a smooth variety. And D now is an effective Q divisor. And S inside X is some smooth hypersurface, some smooth, like a smooth divisor. And assume that S is not contained in the support of D. And I'm going to take T, maybe write it here, T inside S, some closed set. So we wanted to compare the singularities of a pair on S to the singularities of a pair on X. So, and we measure the singularities by minimal lot discrepancy. You look at the minimal lot discrepancy over the set T of S. Maybe I put the application of S dearest to S. That's the pair in one dimension less. And we want to prove that this is the same as the minimal lot discrepancy over T of the pair X, S plus D. I explained already yesterday why S should be there. It's come from adjunction. So maybe I also would like to remark that this theorem holds in larger generality. So I'm really picking the first case where the theorem becomes interesting. It holds when X has locally complete intersection singularities, for instance, but we'll not get there. But already this case has a lot of strong applications. So it's very interesting. So let me now sketch the proof for the remaining part of the talk. So if you remember the discussion we did yesterday, so we look at a common resolution, so resolution of X, which induces a resolution of S. We look at those divisors on X, the divisors on S over S, how they intersect. We have some control. If you think back about what I explained, you see that some inequalities are already there. So what you need to prove in the end is the following, is that if E on some model X prime over X is a divisor such that f of E is contained inside T. I don't really worry too much about that. But and the important condition that we need to focus is the log discrepancy of the pair XD, S plus D is positive, is not negative, then there exists an F inside the resolution S prime of S. And these are maybe not necessarily the same resolution in the diagram before. I may actually need to blow up a little further, but on some resolution there's some F dominating S, like mapping over S, such that, well, the image of F is also contained inside T. And more importantly, the dot discrepancy along F of S and D restricted to S is, let me show I get it right, less or equal than the log discrepancy along E of X, S plus D. So this is really the only thing left to do. Maybe I didn't really explain all the steps to lead to this reduction, but that's really the core of the proof, is to show this statement. So we want to focus on this statement. So let me recall you where the difficulty was. Is that I can realize, I mean, I can, there might be different S, but anyway, so the difficulty, we had this diagram, so we had S, which sits inside X. Over here, we pick up a good resolution, X prime, we look at proper transform that give a good resolution here. Inside here, we have this divisor E. And the problem is that we may have that E is disjoint from S prime. If it's disjoint, then I lose all information. So the idea is to use arc spaces to force these two sets to intersect anyway. So the idea is the following. So I have, let me now turn the diagram around this way. So here I have E and S prime, maybe disjoint. And inside here. But then I can look over here, I look at X infinity. So X infinity gives a different perspective on X from rather than looking at resolutions. And the idea is that inside here, I look at S infinity. That will replace S prime in the resolution. And then what is replacing E? Well, there will be a cylinder C, which is a cylinder of contact 1 with E. So this maximum D0 set. And what we have here, the improvement, is that these two sets are never disjoint. So they do intersect. The reason is that they intersect in a trivial way. On the arc space, there is a natural sister action by reparametrization of the parameters, say t to lambda t. And if you deform this sister action to 0, you see that arcs will deform to the constant arcs. That's essentially all positive degree coefficient to 0. And both sets are stable under this sister action. And of course, they both sets contain some constant arcs on the centers. So they do intersect there. But now you have one of the theorems you learn from in the first course in algebraic geometry is a theorem about intersection of dimension of algebraic varieties. When if two varieties don't intersect, there's nothing you can say. But if they do intersect in projective space, then you can bound the dimension of intersection. So this is what we want to do here. We want to understand how much they intersect now. So let's make some remarks. Well, C inside X infinity is a cylinder. What does it mean it is a cylinder? It means it's defined by finitely many equations. All these equations depend, of course, on finitely many jets. You put back this equation, you get a cylinder. Now we intersect it with S. And it follows that C intersect S infinity is a cylinder. And the reason is very simple. I just take the equations of C, finitely many equations. I restrict this equation to S infinity. They still have finitely many equations that will define a cylinder. Another thing is you look at the equations. You look at the equation cutting S infinity inside X infinity. For instance, if you have a local coordinates, analytically speaking, maybe X has x1 to xn, S is x1 to xn minus 1, then the equation will be xn, xn prime, xn double prime, all equal to 0. So this is form a regular sequence, and I cut down things. So if you just trace that, so I cut down the dimension on the jet schemes, if you like, one by one, every equation. What you do is you restrict this equation to C and see how much you cut down. So by looking at the equation, what you see is that the codimension in S infinity of S infinity intersect C will be bounded above by the codimension of C in X infinity. And the reason why I only have an inequality is that there may be equations of S infinity inside X infinity that vanish identically on C. So if all the equation, every time I impose one of these equations defining S infinity, they cut down properly C, then I see the codimension actually be preserved and will be just an equality. But in general, some of these equations might vanish identically, and therefore I only get an inequality. So what we need to do is simply to estimate the number of such equations. And this is where the evaluation of S comes in. So somehow there is this contribution from S. So we estimate, and we see that there are at least the number valuation along E of S such equation. So this sentence doesn't read very well. It says there are at least K such equations, where K is this number. And so what we get is that the codimension of C intersect S infinity inside S infinity is less or equal than the codimension of C inside X infinity minus this number. So I get an even better estimate. I don't know, maybe there are more, but this is enough for what we want to prove. And remember that this number here is actually equal to KE plus, maybe right, KE over X plus 1. So that's the log discrepancy of E over X. So now I start seeing that these invariants, these numbers that come in a definition of minimal discrepancy, are sort of already contained into the contact set, maximum zero set, as a codimension and as a valuation along the arcs. And now we are ready to finish. So what I'm going to do is that I look at this cylinder. I don't really know that this is irreducible, but what I can do is just take W inside here, be an irreducible component. You will notice that this is also a cylinder. And so what we have is that the valuation along W will be some Q times valuation along some F for some Q greater or equal than 1, and some F on some model S prime over S. And the codimension of W inside S infinity will be at least Q times this KF over S plus 1. So there's a log discrepancy. And now we have all the pieces together. So if you combine everything, so you start combining this inequality with this inequality using these numbers, what you see is that Q times KF of S plus 1, that's this bound this codimension, so they will be less or equal than this number, KE over X plus 1 minus the valuation along E of S. And also what you show is that we have an inequality on evaluations of the divisor D. If I restrict D to S, and I compute the valuation with respect to this valuation here, so they will be greater or equal than the valuation along E of D. So this will maybe require a few steps, but the idea is, again, you go through these contact sets. So The valuation here is determined by valuation along arcs inside W. So you take if you like, you can check on closed arcs and look at the minimum or infimum over there. And well, W is contained inside the set C. So when you try to understand and compare with the valuation of the same divisor on E, along E on X, what you do is that you take a minimum on a bigger set in terms of valuation or order of contact with arcs. And this is where we get this inequality. You get a smaller number potentially. But now if I put these things together, we get that Q times the log discrepancy along F of S and D restricted to S is less or equal than the log discrepancies for E of X. Well, here, these two numbers give me log discrepancies. The valuation of D is determined by this, and what I get is I get this extra number here, which corresponds to adding this divisor here in the picture. And this is an inequality, but now we just conclude that the inequality actually is worked without the Q, using that Q is actually greater or equal than 1, and this number is greater or equal than 0. So if you just put this information in, then you can divide by Q if you like and get the inequality. So this finishes the proof, and it finishes my lectures.
Any questions or comments?
So you did not really use that X is true.
That actually I did use it. So in several places. So one place I use it is that I compute this codimension in terms of log discrepancies. So if X is singular, there is a similar formula, but you need to replace the log discrepancy given by the relative canonical divisor by the order of vanishing of Jacobian. Something that is also known as the matter log discrepancy. So that's already a different invariant, but one can still get a formula using that invariant. But there is another subtle point here, which is this estimation, exactly this formula here. So we are trying to understand how many equations are lost and so on. But in a smooth case, it's easy to make sure that every time I lose an equation, the codimension jumps down by this amount. On the singular case, it's a bit more complicated because the maps on the J schemes, they're not surjective. And in fact, the image is, the only thing I know is that the image is constructible. Now, understanding intersection between constructible set, you understand some condition on the final levels, but then you take inverse image under a constructible image map, and that's like you lose control very quickly of the behavior. Nevertheless, something can be done, and so there is yet another notion of discrepancy. It's called Jacobian discrepancy, which is, let me just actually maybe write it up, what the definition is. You look for a divisor E, you look at the order, what we say, valuation along E or the Jacobian of F. So this is the one coming in the codimension. But then you need to correct this by the order along E or the Jacobian of X. So there is this new contribution coming in. Now, if you look at this invariant, then you get exactly the same theorem.
You need complete intersection to measure to compute the codimension.
So if it is, this is actually equal to the usual discrepancy if it's a locally complete intersection. So in the locally complete intersection, this theorem is true. That's not the original proof, but you can prove it actually this way, just the same proof. Actually, in fact, this is not the original proof anyway. And in a singular case, what you need to recognize is that when it's not locally complete intersection, these two actually start differing, they start being different, and this is the right invariant to look at. Thank you.